Chapter 11, Wildlife and Pollution. Edited by Peter Moyle and Douglas Skelt. By J. Davis. Introduction. Pollution is one of the primary ways in which humans have caused drastic modifications of wildlife habitat. Historically, we have regarded the air, water, and soil that surround us as waste receptacles, and have given little consideration to the ecological consequences of our actions. As a result, wildlife populations are confronted with a bewildering array of pollutants that we release into the environment, either by intent or accident. In some cases, wildlife populations have suffered severe losses, or even faced extinction due to pollution. For example, the bald eagle, peregrine falcon, and brown pelican all nearly became extinct before scientists discovered that the synthetic chemical DDT was the cause of devastating reproductive failure in these species. Oil spills, such as the fouling of the coast of southern Alaska by the grounding of the Exxon Valdez, take an immediate toll on many species, with the misfortune of living near such blunders. Toxic metals can kill adult members of wildlife populations, and cause the production of deformed offspring, as seen at Kesterson Reservoir in the San Joaquin Valley. Acid rain has caused hundreds of fish populations to disappear from lakes in the northeastern U.S. and Scandinavia. In this chapter, each of these notorious instances of the impacts of pollution on wildlife are described. The chapter also provides a general discussion of the origins and effects of synthetic chemicals, oil spills, toxic metals, and acid rain. What is pollution? Pollution can be defined as the human alteration of chemical or physical characteristics of the environment to a degree that is harmful to living organisms. Some forms of pollution exert a destructive influence on wildlife by killing or impairing the health of individuals. Synthetic chemicals, oil, toxic metals, and acid rain are included in this category of toxic pollutants. Other forms of pollution affect wildlife in a more indirect manner, by altering or destroying wildlife habitat. Examples include the obliteration of canyons, marshes, and grasslands with solid waste landfills, the destruction of the ozone layer by chlorofluorocarbons, which may lead to widespread damage due to the effects of excessive ultraviolet radiation on wildlife and their food sources, and carbon dioxide accumulation in the atmosphere, which may lead to global changes in climate and the distribution of wildlife habitats. Although both of these categories of pollutants pose significant threats to wildlife, this chapter focuses on toxic pollutants because of their specific effects on wildlife. Different species vary in their sensitivity to toxic pollution. For example, populations of fish living in lakes in the northeastern U.S. have proven to be extremely intolerant of the increased acidity caused by acid rain. On the other hand, fish populations in naturally acidic Florida lakes thrive under conditions that would kill fish from northeastern lakes. Why are some fish populations sensitive to the effects of acidity, while others are tolerant? The process of evolution allows species to optimize their chances of survival by adapting to the biological, chemical, and physical characteristics of their environment. Evolution, however, occurs over the course of many generations. Over thousands of years, fish populations have evolved a tolerance of the conditions in the naturally acidic Florida lakes. Fish in northeastern lakes have evolved to survive under very different conditions, and have no mechanism for coping with high levels of acidity. In recent times, humans have released thousands of synthetic chemicals into the environment, and altered the distribution of many naturally occurring substances, thereby creating conditions that wildlife species had never experienced before. In many instances, these new conditions have disrupted the delicate biological machinery evolved by organisms over thousands of years. Synthetic chemicals. The use of synthetic chemicals to control pests, principally insects, weeds, and fungi, became an integral part of agriculture and disease control after World War II. These chemicals were credited with providing an inexpensive means of increasing crop production, preventing spoilage of stored foods, and saving many millions of human lives by the prevention of certain insect-borne diseases. The history of DDT use in the U.S. is symbolic of the gradual development of an awareness of the ecological consequences of pesticide application. DDT was one of the most widely used pesticides in the post-war era. The first significant applications of DDT, in the 1940s, saved millions of human lives from malaria, typhus, and other deadly diseases. DDT was considered such an extraordinarily valuable substance, that in 1948, the Nobel Prize in Medicine was awarded to Paul Mueller, the Swiss chemist who discovered the compound's insecticidal properties. By 1964, DDT was so broadly applied, that annual production in the U.S. reached 90 million kilograms. By the late 1960s, however, Wildlife biologists realized that DDT was producing disastrous side effects in wildlife species. In the 1970s, most industrialized countries banned the use of DDT because of its unacceptable effects on wildlife and, ultimately, humans. DDT is classified as an organochlorine chemical, a descriptive label that reflects its chemical structure, consisting of a combination of carbon. Organic molecules are defined as those comprised of at least some amount of carbon, and chlorine atoms. Other organochlorines, that are important environmental pollutants, include polychlorinated biphenyls, PCBs, and dioxins. PCBs were used as insulators in the electrical industry, until the environmental threat posed by their toxicity was realized in the mid-1970s. Dioxins are the most potent chemical carcinogens, cancer-causing substances, known, and are present in the environment largely as a byproduct of various industrial activities, for example, bleaching of paper. The properties that make DDT, and other organochlorine pesticides, toxic to insect pests, also make them hazardous to wildlife. The most important property of a pesticide, of course, is that it has a deleterious, or toxic, effect on pests. Unfortunately, it is difficult to formulate chemicals that exert toxic effects in pests alone. Another important property of a pesticide is that it persists long enough after application for pests to encounter it. Organochlorine pesticides are extremely persistent. For example, some of the DDT applied in this country in the early 1970s is still present in the environment today. An additional important characteristic of organochlorines is their tendency to be accumulated by living organisms. Organochlorines are strongly attracted to fats present in cells and tissues of living organisms. Since organochlorines resist degradation, these compounds can gradually accumulate to high concentrations in tissues of vertebrates. The chemical characteristics of organochlorines have led to their distribution across the entire globe. Risber 1968. Organochlorines have a slight tendency to vaporize and become suspended in the atmosphere. Once this occurs, organochlorine molecules are subject to air movements that may transport them to any part of the Earth's surface, including remote oceanic and polar regions. Due to their broad distribution via atmospheric transport, trace amounts of organochlorines are present in all vertebrates, including humans. It is thought that virtually every person in the U.S. is exposed to dioxin on a daily basis. Travis 1989. Trace quantities of DDT, PCBs, and other organochlorines are commonly present in human tissues. While the use of DDT, and other organochlorine compounds, has been curtailed in the U.S. and other developed countries, their use in developing nations continues, particularly in efforts to control the spread of human disease. However, the evolution of resistance to DDT by many insect pests has sharply reduced its effectiveness, and eventually its complete replacement by other pesticides is expected to occur. Other types of synthetic insecticides have been developed that pose lesser environmental threats than the organochlorines. Organophosphates, with the chemical structure consisting of carbon and phosphorus atoms, are now widely used. These compounds degrade much more readily than the organochlorines, and therefore have less of an impact on non-target species. Malathion, large quantities of which have been used in attempts to control the Mediterranean fruit fly in California, is a well-known organophosphate insecticide. Other synthetic pesticides are used to control weeds, fungi, and other pests. Although these more recent generations of chemicals pose less of an ecological threat than the organochlorines, they still have been shown to produce adverse effects in wildlife populations. Because annual rates of overall pesticide application show no sign of decreasing, Figure 11.1, wildlife populations will continue to be affected by exposure to pesticides. Figure 11.1. Pesticide use in the U.S. has more than doubled since 1965, but leveled off somewhat in the early 1980s. From Postel, 1987. The most widespread effects of synthetic chemicals on wildlife have been caused by organochlorines. One of the reasons that organochlorines have proven so potent is their tendency to reach progressively higher concentrations, with increasing level in the food web, a process known as biomagnification. Clear Lake, California, was the site of the first study demonstrating the occurrence of organochlorine biomagnification, Hunt and Bischoff 1960. The periodic appearance of teeming populations of gnats during the summer had annoyed Clear Lake residents for many years. Studies of methods of controlling the gnats began as early as 1916. Although use of pesticides to kill the gnat larvae, and use of native fish to consume them, were both explored, neither of these techniques were effective. In 1949, lake managers decided to use the newly developed organochlorine pesticide EDD, closely related to DDT, which preliminary experiments showed to be very potent to gnat larvae, yet relatively harmless to fish. The first large-scale DDT treatment of Clear Lake was made in 1949. Very few gnats were observed until 1951, when their numbers again began to increase. In 1954, DDT was again applied to the lake, this time in a 50% stronger dose. 2 months after the second application, 100 western grebes, a fish-eating bird, were found dead on the lake, showing no symptoms of infectious disease. Gnat populations rebounded again in 1955 and 1956, resulting in a third treatment of the lake in 1957, at the same dosage used in 1954. 2 months later, 75 grebes were found dead on the shores of Clear Lake. Chemical analysis of tissue from these birds revealed the presence of extremely high concentrations of DDT. As a result of biomagnification, DDT concentrations in fish and birds from Clear Lake were 80,000 times higher than the concentrations in water, figure 11.2. By 1960, the breeding population of grebes, which numbered 1,000 pairs before the spraying began in 1949, had disappeared. Only recently has the population been able to re-establish itself. Figure 11.2. Top, applying DDE, a breakdown product of DDT, to Clear Lake, 1950s. Bottom, concentrations of DDE in western grebes on Clear Lake reached concentrations 80,000 times higher than those in water. This was the first demonstration of the biomagnification of pesticides in food chains. After Connell and Miller, 1984. During the 1950s, the use of organochlorine pesticides expanded rapidly throughout the world. Biomagnification of organochlorines, subsequently, was found to be occurring worldwide. By the late 1960s, it became evident that the high DDT concentrations observed in many bird species were at least partially responsible for their declining populations. The decline of the peregrine falcon in Great Britain and North America initiated widespread concern over the possible link between organochlorine pesticide use and adverse ecological effects. By 1975, the peregrine had vanished from the eastern U.S., and remnant populations in the USA remained only in the Rocky Mountains and California. In the late 1960s, researchers recognized a relationship between DDT contamination and eggshell thickness in peregrines and other breeding birds. The chemical structure of DDT resembles the structure of female reproductive hormones, called estrogens, that mediate the process of eggshell formation. In some birds, DDT interferes with the activity of estrogens, resulting in the production of abnormally thin eggshells that are highly susceptible to breaking under the weight of incubating parents. Organochlorines were linked to eggshell thinning in raptors, such as peregrine falcons, bald eagles, and ospreys, and fish-eating birds, such as brown pelicans, and double-crested cormorants, Anderson and Hickey 1972. The strongest evidence that organochlorines were a significant factor in pushing peregrines, bald eagles, and brown pelicans, each of which is an endangered species, toward extinction, is the simultaneous recovery of these species since the 1972 ban of DDT use in the US and Europe. DDT has also been shown to exert other effects in bird populations. Gulls are resistant to eggshell thinning, but exposure of male gull embryos to elevated concentrations of DDT can result in abnormal development of their reproductive organs, and markedly affect their reproductive behavior when they mature. The estrogenic activity of DDT can cause these birds to develop and behave like feminine males. It is likely that exposure of male gull embryos to DDT, and other similar organochlorines, contribute to the distinctly skewed sex ratios, with females far outnumbering males, observed in breeding colonies of gulls in many parts of North America, Fry 1987. It appears that males in these populations are incapable of reproducing, and avoid the breeding colonies. Obviously, rates of reproduction in these populations are far below normal, and as a result, populations may remain suppressed for many years after exposure to the pollutants ceases. Evidence also exists, suggesting that biomagnification of other organochlorines is affecting wildlife populations. For example, PCBs are the suspected cause of decreased hatching success, abnormal parental behavior, and developmental abnormalities in Forster's tern. Kubiak 1989. In one of the few cases demonstrating the effects of toxic pollutants on mammals, domestic mink, raised for fur, feeding on fish from the Great Lakes, have also been shown to accumulate toxic concentrations of PCBs. Marine mammals also accumulate concentrations of organochlorines in their fat tissue, that are thought to adversely affect their reproduction. Fish are known to exhibit biochemical responses to PCB concentrations in their tissues, but the ecological consequences of this contamination are unclear. Although the effects of synthetic chemical pesticides on wildlife are typically the result of long-term exposure via the food web, wildlife populations can also suffer from direct exposure, primarily during pesticide application. Aerially sprayed substances are especially susceptible to drifting, and affecting wildlife, including birds, mammals, and fish, in areas bordering cropland. Agricultural pesticide application is one of the principal causes of fish kills in the United States. Accidental releases of pesticides also occur occasionally. An example was the release of 30 tons of insecticides, herbicides, and fungicides into the Rhine River in Switzerland in 1986, which killed an estimated 500,000 fish. Recovering from pesticide abuse, the California brown pelican. Flocks of brown pelicans flying in linear formation near the surface of the ocean are a fairly common sight along the California coast today. These birds can also be seen fishing, dive-bombing the water surface, and emerging with their catch. In the late 1960s and early 1970s, DDT contamination caused this acrobatic species to come dangerously close to disappearing from the California coast. Figure 11.3 Brown pelicans. California Academy of Sciences. The primary breeding grounds of the California brown pelican are California's Channel Islands and other islands along the shores of Baja California and mainland Mexico. These colonies experienced widespread reproductive failure due to the effects of DDT in the late 1960s and early 1970s. A corresponding decline was noted in populations of the eastern brown pelican along the southeastern and Gulf coasts of the United States. Because of these declines, the brown pelican was classified as endangered by the U.S. Fish and Wildlife Service in 1970. During this period, the coastal waters of Southern California contained levels of DDT that were among the highest recorded anywhere in the world. The source of this contamination was determined to be a DDT manufacturing plant that was introducing massive quantities of this substance into the Los Angeles sewer system. Since the Los Angeles sewage is piped several miles offshore to be discharged, DDT contamination extended far from its point of origin. In a 1969 survey of the main breeding colony in the Channel Islands, crushed eggs were found in many nests, and the colony was littered with broken eggshells. Shell fragments were determined to be 50% thinner than normal. These shells were too thin to withstand the weight of incubating parents. High concentrations of DDT were also found in a sample of the few eggs that had not been crushed, and subsequent studies demonstrated that DDT was the cause of the eggshell thinning. In 1969, only 4 young fledged from the 750 nests built in the Channel Islands. In 1970, 552 nests yielded only 1 young pelican. Low productivity of the Channel Island colonies continued through 1973. In 1970, the DDT manufacturer began to dispose of its liquid wastes at a landfill instead of in the sewer system. This led to a reduction in DDT concentrations in coastal waters, an increase in eggshell thickness, and improved breeding success, beginning in 1974. Breeding success generally continued to improve into the 1980s, with abundance of the pelican food supply, northern anchovy, replacing DDT as the most important controlling factor. Fortunately, the effects of DDT on reproduction in brown pelicans were realized in time to prevent their extinction. Oil spills. Modern society relies heavily on the use of fossil fuels, i.e., oil and coal, not only as a source of energy, but also as a raw material for many products, including synthetic chemicals, plastics, and styrofoam. Fossil fuels are comprised primarily of compounds called hydrocarbons. Hydrocarbons are molecules comprised largely, as their name suggests, of hydrogen and carbon. Hundreds of different hydrocarbon molecules exist, due to variation in the number and arrangement of these atoms. Hydrocarbons yield large quantities of energy when they are burned. About 50% of the worldwide use of petroleum is attributed to countries in North America and Europe, even though these countries hold only 14% of the world's population. Because of this arrangement, massive quantities of oil are transported around the globe every year. The primary methods of transporting oil are oceanic tanker and overland pipeline. A seemingly inescapable consequence of these transport activities is the accidental spillage of oil, occurring at the site of oil extraction, i.e., oil platform blowouts, in transit, tanker accidents, or even after delivery to refineries. A local example of the latter type of accidental spill occurred in 1988, in San Francisco Bay, when negligent workers at the Shell refinery in Martinez allowed over 400,000 gallons of crude oil to flow into the bay. The most obvious effects of oil spills on wildlife are the deaths that occur immediately after the spill, due to coating of animal fur or feathers with oil and exposure to high concentrations of the toxic components of crude oil. These effects may be assessed by estimating the numbers of animals killed immediately following a spill. When birds and mammals become coated with oil, the insulating property of their feathers or fur is lost. Feathers and fur provide insulation by trapping a layer of air between the skin and the external environment. Oiling disrupts the arrangement of feathers and hair that retains this insulating layer. In Arctic environments, the resulting hypothermia contributes to the death of many animals. It is usually impossible to distinguish the effects of hypothermia from the effects of exposure to the toxic components of petroleum. Crude oil is a complex mixture of organic and inorganic chemicals that varies widely in its composition. Some types of hydrocarbons present in petroleum are toxic to wildlife, and direct exposure to crude oil can cause toxic effects. Oiled animals are exposed to acute doses of hydrocarbons absorbed through their skin, inhaled, or accidentally swallowed. Oiled animals also intentionally swallow the toxic material, as they preen their bodies. Animals that are recovered and examined often suffer from a multitude of symptoms due to the inundation of their internal organs with toxic chemicals. The long-term effects of oil spills are far more subtle and difficult to assess than the short-term effects. The presence of persistent toxic chemicals on the beaches, in the water, and in the food web, may result in a variety of impacts on wildlife, including impaired reproduction, decreased resistance to disease, anemia, eventual development of cancerous tissue growth, particularly in fish, neurological damage, and birth defects in offspring. The extent to which such effects occur in the years after an oil spill is largely unknown. The Exxon Valdez oil spill. In March 1989, a tanker laden with crude oil from Prudhoe Bay, Alaska, ran into a reef in Alaska's Prince William Sound, and 11 million gallons of crude oil spilled into one of the nation's most pristine and productive coastlines, Figure 11.4. The wreck of the Exxon Valdez caused the worst oil spill ever to occur in North American waters. The Exxon Valdez spill occurred in an area noted for the diversity and abundance of seabirds, marine mammals, fish, and other wildlife. The magnificent qualities of the region affected by the spill are evidenced by the fact that it includes 3 national parks, 4 national wildlife refuges, and a national forest. Eventually the spill spread over an estimated 1,400 miles of shoreline, enough to blacken every bay, beach, and estuary in California. Many factors contributed to the magnitude of this ecological disaster, including negligence on the part of the officers of the Exxon Valdez, and a lack of preparedness on the part of Exxon and governmental agencies. However, the underlying cause of the spill was the demand for oil that drew the Exxon Valdez toward the Exxon refinery in Benicia, California. Figure 11.4. Oil from the Exxon Valdez oil spill affected 1,460 miles of Alaskan coastline. Inset shows the size of the Exxon Valdez oil spill relative to the California coastline. A total of 36,466 dead seabirds, 1,015 dead sea otters, and 144 dead bald eagles were recovered from the spill area. For several reasons, these statistics are not indicative of the total numbers of animals that died. Many of the 1,400 miles of affected shoreline consist of inaccessible or poorly mapped areas that could not be investigated. Furthermore, many animals that were killed were never recovered. Some species, such as harbor seals, sink when they die, and therefore are not represented at all in the mortality counts. Actual mortality of oiled birds probably exceeded 100,000, the highest losses of birds recorded for any oil spill, Henham in 1989. Murres, a genus of seabirds in the auk family, comprise the majority of recovered seabirds. These birds had concentrated for breeding at the Barren Islands, approximately 200 miles southwest of Valdez, and suffered heavy mortality when large slicks stalled there in early April. Bald eagles were also exposed to the oil, as they scavenged dead otters and birds, both oiling their feathers and ingesting oil in the process. Most of the dead eagles were recovered from beaches, many more probably died at their roosts away from the shore. A high percentage of bald eagle nests were inactive in the summer of 1989, but this may be partially attributable to human disturbance relating to cleanup of the spill. Sea otters, Figure 11.5, reside year-round in the waters affected by the Exxon Valdez spill. A population of 2,000 to 4,000 otters inhabited Prince William Sound before the spill. Most of the 1,015 dead otters had been members of this population. Other marine mammals that reside in the spill area include harbor seals and Steller sea lions. Although individuals of these other species, and some of their haul-out sites were oiled, no oil-related effects were apparent. Several species of whales also frequent the area affected by the spill, but again no obvious effects on these species were observed. Figure 11.5. Sea otter soaked in oil after Exxon Valdez spill. Exxon Valdez Oil Spill Trustee Council. A wide variety of land mammals use the shoreline of the spill area. River otter and mink are thought to be the terrestrial species most affected by the spill. Both river otter and mink feed on fish and invertebrates present in the intertidal zone. Several dead individuals of these species were recovered, and at least some of these deaths are thought to be due to exposure to oil. Other terrestrial species, including bears and foxes, scavenge dead birds and otters that washed up onto beaches. Prince William Sound is the site of a lucrative commercial fishery, valued at over $110 million, in 1988. The principal fisheries are salmon and herring. Major commercial fisheries in spill-affected portions of the Gulf of Alaska, outside the Sound, exist for salmon, Pacific cod, Pacific halibut, Pacific ocean perch, sablefish, and walleye pollock. The value of the commercial salmon fishery alone was $308 million in 1988. Recreational fishing is also intense in this region. As might be expected, the effects of the spill on fish, especially in Prince William Sound where the effects of the spill were most severe, are a matter of grave concern. The impact of the spill on young salmon and herring, the two most important commercial species in the Sound, was a matter of particular concern. Salmon in Alaskan waters spawn in freshwater in the fall, and then die. Their eggs develop during the winter, and in the spring the fry emerge, and head toward the Sound. Many fry are also released from hatcheries. The spill occurred as the salmon fry were entering Prince William Sound. Although great efforts were made to prevent contamination of fry in the Sound, it is likely that some spill-related mortality occurred. Herring spawn in the Sound, between April and June, depositing their eggs on intertidal and subtidal marine plants in several areas that were heavily oiled. Adult herring appeared not to be deterred from their spawning areas by the oil. It is likely that significant mortality of their eggs occurred. The long-term effects of the wreck of the Exxon Valdez will be difficult to determine, and studies are still ongoing. A problem that plagues studies of the effects of pollution on wildlife is that it is extraordinarily difficult to distinguish some of the subtler effects of pollution on populations from the multitude of natural factors that also influence populations. For example, the long-term effects of the Alaskan oil spill on the salmon and herring populations is obscured by the effects of weather, varying food supplies, fishing, and perhaps other sources of pollution that may be present in Alaskan waters. Toxic metals. Toxic metals, Table 11.1, are natural components of the Earth's crust, found throughout the ecosphere in at least small, or background, concentrations. These background concentrations are harmless to living organisms. Human activities, however, can cause concentrations of toxic metals to reach levels that pose hazards to living organisms. Some of these activities include burning of fossil fuels, metal refining, agriculture, mining operations, and wastewater discharge. For most of the toxic metals, the quantities of these substances mobilized by humans far outweigh the amounts that would naturally cycle through air, soil, and water of the earth. Nraigu and Pakina 1988. Toxic metals are present in oil and coal, and metal-contaminated particles are released into the atmosphere by combustion of these fuels. A small fraction of these particles, however, becomes suspended in the upper atmosphere, and is transported great distances from its source. As a consequence of this long-range transport, unnaturally high concentrations of toxic metals have been found in glaciers and lake sediments, in the most remote regions of the Northern Hemisphere. Schindler 1988. Table 11.1. A list of common toxic metals: aluminum, arsenic, cadmium, chromium, cobalt, copper, iron, lead, molybdenum, nickel, selenium, silver, tin, and zinc. In urban areas, industries and automobiles release large amounts of toxic metals into the air, that eventually settle onto the ground. During rainstorms, water picks up these pollutants as it flows over the ground surface. This stormwater runoff ultimately flows either into a local sewer system, or a local water body, in other words, creek, stream, river, lake, estuary, or ocean. Stormwater runoff from urban areas is one of the most significant sources of toxic water pollution, including pesticides from lawns and home gardens. The use of lead as an anti-knock agent in gasoline, which began in 1923, greatly increased the amount of lead released into the environment via automobile exhaust. Combustion of leaded gasoline resulted in widespread contamination of terrestrial and aquatic ecosystems, particularly near roads with dense traffic. Wildlife living near roads have been shown to accumulate elevated concentrations of lead. Clark 1979. Lead is extremely toxic to mammals, including humans, and birds. The effects of lead on the neurological development of humans is the primary reason that the use of leaded gasoline has been curtailed dramatically in the last 20 years. Lead concentrations in urban regions have declined as a result. Agricultural practices that have led to environmental contamination by toxic metals include the use of pesticides and fertilizers that contain these substances, and irrigation, particularly in dry regions of the western United States, which leaches the substances, for example, selenium, from soils. Mining operations expose ore deposits and waste rock to weathering, resulting in the formation of acid mine drainage. Acid mine drainage is a significant source of toxic water pollution in regions where substantial mining has occurred, such as the Sacramento Valley Basin. For example, the Iron Mountain Mine, now closed, is a huge devastated area that drains into the Sacramento River near Redding, carrying with its drainage water a toxic brew of heavy metals. The toxic water is stored behind an earthen dam, and is trickled into the river when flows are high, using dilution to reduce toxic effects. The potential for a major toxic spill, for example, if an earthquake destroys the earthen dam, is high, which could result in devastation of the river's already beleaguered salmon runs, as well as contamination of a substantial portion of the state's drinking water. A wide variety of materials used by society contain toxic metals, and, because discharge into the environment is a widely practiced form of modern waste management, hazardous concentrations of toxic metals can be found in some locations. Household and industrial wastewater often carry high concentrations of toxic metals into aquatic environments. Various products used in households that are washed down drains and flushed down toilets, such as laundry detergents, bleaches, bathroom cleansers, and even shampoos, contain measurable quantities of toxic metals. Plumbing systems with metal components are an additional source of toxic metals to household wastewaters. An even larger array of solvents, cleansers, and other chemicals are used in industrial activities, and contribute quantities of toxic metals and other pollutants to industrial wastewaters. The effects of lead on waterfowl was one of the earliest documented cases of the effect of a toxic metal on wildlife populations. One source of lead that is of great significance to bird populations is the use of lead shot by North American duck hunters. Prior to 1991, an estimated 3,000 tons per year of lead was deposited by duck hunters. Ducks, geese, and other water birds pick up these lead pellets while feeding. Approximately 2 to 3% of the North American waterfowl population, or as many as 2 million ducks and geese, died from lead poisoning each year. Upland game birds, such as mourning doves, have also been shown to accumulate lead in their tissue due to ingestion of lead shot. Species that feed on waterfowl, such as bald eagles, may also be exposed to high concentrations of lead and suffer the effects of lead poisoning. Although steel shot is a non-toxic alternative to lead shot, hunters resisted switching to steel shot, arguing that it is less effective at killing birds, damaging to guns, and prohibitively expensive. Nevertheless, in 1986, the Secretary of the Interior announced that lead shot would become illegal for waterfowl hunting beginning with the 1991 season. In Mexico and other countries, however, lead shot is still used, and waterfowl continue to be exposed to lead during their annual migrations. Toxic metal emissions from metal smelters have been shown to exert adverse effects on wildlife populations. Metal smelters release pollutants into the atmosphere through tall smokestacks. Toxic metals, and other pollutants, gradually fall to the earth downwind of the stack. Studies have shown that severe environmental contamination can occur close to the source, damaging both plant and animal communities. Friedman 1989. Concentrations of several metals have been shown to accumulate in small mammals, such as shrews and mice, and in various bird species, downwind of smelters. Selenium and Kesterson Reservoir. One of the most dramatic cases of toxic metal contamination known to date involved the accumulation of toxic concentrations of selenium at Kesterson Reservoir in California's San Joaquin Valley. Reduction of California's historic wetland habitat, coupled with the scarcity and high cost of water, created interest among wildlife resource managers in using agricultural drainage for the creation and maintenance of wetlands. The Kesterson Reservoir was created in the late 1960s, as part of a comprehensive scheme for managing agricultural drainage in the San Joaquin Valley. Water flow into the reservoir began in 1972. The reservoir was intended to provide for storage and evaporation of agricultural drainage, and for establishment of wetland habitat. Kesterson was actually added to the National Wildlife Refuge system because of its perceived value as wildlife habitat. The coastal mountains that form the western boundary of the San Joaquin Valley consist of rocks, shales, that are relatively enriched with selenium. Irrigated agriculture on poorly drained soils, in the arid San Joaquin Valley, can cause selenium to become highly concentrated in agricultural drainage. By 1981, almost all of the flows into Kesterson consisted of agricultural drainage, originating from such poorly drained soils. In 1982, mosquito fish collected from Kesterson were found to contain concentrations of selenium nearly 100 times higher than those in mosquito fish from nearby wetlands, at Volta National Wildlife Refuge, that did not receive agricultural rainwater. The U.S. Fish and Wildlife Service, USFWS, followed up on this finding by conducting several studies in 1983 to 1985, to determine whether selenium, or other contaminants, were present at concentrations that could harm wildlife. Results of measurements of selenium concentrations in various components of the Kesterson ecosystem are shown in Figure 11.6. Plants and animals in Kesterson Reservoir, that serve as foods for waterbirds, were found to contain remarkably high concentrations of selenium. Concentrations in water entering Kesterson Reservoir averaged about 0.3 parts per million. Average selenium concentrations were much higher in algae, 69 parts per million, and aquatic plants, 73 parts per million, than those in water. Aquatic insects contain more than 100 parts per million. Mosquito fish contained an average of 170 parts per million, or over 500 times the concentration in water. All of these concentrations were much higher than those measured in wetlands at Volta. As a consequence of the high concentrations of selenium in their foods, waterbirds at Kesterson accumulated levels in their tissue that had devastating effects on their survival and reproduction. Hundreds of adult birds died due to the acute effects of selenium toxicity. Some of the symptoms observed in these birds were severe emaciation, muscle atrophy, liver degeneration, and abnormal loss of feathers. Some adult birds tolerated the contamination well enough to survive and attempt to reproduce, but their offspring were often stillborn or deformed. Developmental abnormalities in embryos included missing or abnormal eyes, beaks, wings, legs, and feet. Figure 11.6. Approximately 540 failures, dead or deformed offspring, out of 2,689 eggs, 20%, were attributed to the toxic effects of selenium. Overall, at least 1,000 migratory birds, adults, embryos, and chicks, died at Kesterson, during 1983 to 1985, as a probable result of feeding on plants, invertebrates, and fish with elevated selenium concentrations. Figure 11.6. Selenium concentrations reach toxic levels in blackneck stilts, and other water birds at Kesterson Reservoir. Accumulation of selenium by algae caused contamination of the plant or animal foods, of several bird species. Data from Ohlendorf, 1989. Figure 11.7. Selenium at Kesterson Reservoir had a devastating effect on reproduction in several bird species. Blackneck stilt embryos collected at Kesterson Reservoir, A normal embryo, and B, an embryo with deformed eyes, beak, legs, and feet. Photos courtesy of Harry Ohlendorf. As a result of this disaster at Kesterson, millions of dollars have been spent in studies of the occurrence and effects of selenium in the San Joaquin Valley, and on the cleanup of the contamination at Kesterson. Events at Kesterson also have intensified pressure to find a solution to the problem of disposing of the salty, pollutant-laden waters that flow from irrigated farmland and arid environments. The circumstances that combine to create problems at Kesterson are not unique to the western San Joaquin Valley. Seleniferous soils are farmed throughout the arid western United States. Recently, selenium-contaminated ponds in the Tulare Basin, part of the southern San Joaquin Valley, have also been discovered to host populations of waterbirds that are producing deformed offspring. Over 60% of the 4,190 acres of these ponds in the Tulare Basin are thought to pose a serious threat to breeding waterbirds, Skorupa and Roster 1990. Similar problems are present in other wildlife refuges in the West that use water that drains from irrigated fields. Acid rain. Although acid rain presently is one of the most familiar forms of environmental pollution, the potential hazard posed by acid rain was first recognized only 20 years ago. By the late 1970s, public concern over the effects of acid rain on aquatic and terrestrial ecosystems had become widespread. At that time, some respected researchers still contended that there was no reason to believe that pollutants were the chief reason for acidification of surface waters. In order to settle this controversy, President Carter, in 1980, initiated a 10-year program to study the causes and effects of acid deposition and strategies for its control. The National Acid Precipitation Assessment Program, NAPAP, is presently drawing to a close after an expenditure of $500 million, making it one of the largest research efforts in history. Many of the more than 1,000 researchers employed through NAPAP will soon have to find a new line of work. The evidence is now thoroughly convincing that pollutants emitted during fossil fuel combustion are responsible for acidification of lakes and streams in the eastern United States. Acid rain is primarily caused by the release of sulfur and nitrogen into the atmosphere as a result of the combustion of oil and coal by power plants and automobiles. Acid rain is actually only one of several ways in which the acidity of aquatic ecosystems can be increased. Acid snow and acid fog also have been shown to occur. Acidic particles suspended in the atmosphere, and gaseous forms of acids, collectively referred to as dry deposition, are also known to contribute to acidification of surface waters. In the following discussion, the term acid rain will refer to all of these various forms of unnaturally acidic deposition from the atmosphere. Acidification can also occur due to other sources, an important one being acid mine drainage. Broad regions in northern Europe and eastern North America have been known for a relatively long time to have acidic rainfall. More recently, acid rain has been found in western North America, Japan, China, the Soviet Union, and South America. In areas where acid rain threatens aquatic ecosystems, the source of the acidity is principally fossil fuel combustion. The pattern seen in eastern North America, for example, results largely from the presence of large coal-burning power plants in the Midwest. These plants use tall smokestacks to avoid causing unacceptable air pollution in their local region. The tall stacks allow the plumes to be dispersed into currents in the atmosphere that can carry the acids and other pollutants for hundreds of miles. Much of the acidity found in rainfall in Pennsylvania, New York, and eastern Canada is due to the emissions of power plants in the Midwest. Similarly, much of the acidity found in rainfall in Scandinavia originates in industrial areas of Central Europe and the United Kingdom. Polluted air masses have been tracked across the Atlantic Ocean and over the North Pole, from Europe and Asia to North America. As for organochlorines and toxic metals, which are also subject to long-range atmospheric transport, no site anywhere in the world is entirely free from deposition of acidic pollutants. When rain falls to the land surface, gravity draws the water toward areas of low elevation. Water bodies, such as streams, rivers, and lakes, form in these low areas. The land area that drains toward a given water body is known as a drainage basin, or watershed. Some drainage basins contain rock formations that can neutralize the acidity of rainwater as the water flows through the basin. Some drainage basins, however, do not reduce the acidity of runoff. Water bodies in these drainage basins are susceptible to accumulation of acidity. These water bodies, and their associated drainage basins, are known as acid-sensitive regions. Acid-sensitive regions are more widely distributed in the U.S. than previously thought, occurring in the upper Midwest, several southeastern states, and many mountainous areas of the West. In addition to the well-known northeastern part of the country, a combination of both acidic rainfall and an acid-sensitive drainage basin are required for acidification of an aquatic ecosystem to occur. The potentially deadly combination of acidic rainfall and sensitive drainage basins occurs in many water bodies in the northeastern U.S. and Scandinavia, where hundreds of lakes have completely lost their fish populations. Approximately 100 lakes, in the Adirondack Mountains of New York, are fishless due to the effects of acid rain. In southern Norway, an astonishing 700 lakes are fishless due to acid rain. In many other lakes, fish populations are declining. The Adirondack lakes are estimated to have lost at least 98 brook trout populations, and many populations of other species, including lake trout, rainbow trout, white sucker, brown bullhead, pumpkin seed sunfish, and golden shiner. Haynes and Baker 1986. As the acidity in vulnerable water bodies increases, sensitive species of fish, and other organisms, begin to lose their ability to reproduce and survive. Juvenile fishes, and many organisms lower in the aquatic food web, are particularly sensitive to the effect of increasing acidity. The early disappearance of organisms eaten by large predatory fish is thought to be a primary explanation for crashes in fish populations. Direct toxicity to adult and juvenile fish is another important factor in these declines. The toxic effect of acid rain on fish is due both to the acidity itself and to other substances, For example, aluminum, some forms of which are toxic, that are formed, or released under acidic conditions. Creative solutions to pesticide pollution. Since the discovery of some of the adverse effects of indiscriminate pesticide usage in the 1970s, alternatives to total dependence on chemicals to control pests have been adopted by farmers. A guiding philosophy known as integrated pest management, IPM, underlies most strategies to reduce pesticide use. In IPM, an agricultural field is viewed as an ecosystem containing pest populations that are influenced by many interacting natural forces. IPM makes use of several types of techniques to minimize damage caused by pests, including biological controls, cultural practices, genetic engineering, and judicious use of chemicals. A biological control can include introducing, or enhancing, populations of natural predators. The use of natural substances to interfere with pest life cycles, such as the use of sex attractants to draw pests to traps, is another type of biological control. Cultural practices are farming techniques, such as planting patterns, that interfere with pest life cycles. Genetic engineering can be used to develop pest-resistant crop varieties. Under this integrated approach, farmers use chemicals only when necessary, rather than as the first, and primary, line of attack. One of the central principles of IPM is that pest populations must be maintained at some minimal level, in order to maintain populations of predators. Traditional methods of pest control, on the other hand, aim to eradicate pest populations entirely. Successful eradication, however, also reduced predator populations, thereby creating an ecologically unstable situation. Governmental programs encouraging the adoption of IPM were initiated in the 1970s. As of 1984, IPM programs supervised by the U.S. Department of Agriculture Extension Service were underway for nearly 40 crops, and collectively covered 11 million hectares, about 8% of the nation's harvested cropland. During the period 1971 to 1982, for example, U.S. pesticide applications on fields of sorghum, cotton, and peanuts declined 41%, 75%, and 81%, respectively, Postil 1987. Successful application of IPM requires knowledge and ingenuity. The pest's life cycle, behavior, and natural enemies, the influence of planting patterns, and chemical use on pest and predator populations, and many other aspects of the agricultural ecosystem, must be understood in depth. IPM offers several benefits, including a decreased reliance on costly chemicals, reduced health risk from exposure to chemicals, either during pesticide application, or by contamination of groundwater supplies, and diminished impacts on non-target wildlife populations. Farmers adopting IPM have been shown to spend less money on pest control. For example, the Texas cotton farmers, mentioned previously, had net returns per hectare averaging $282 higher than other cotton farmers, Postil 1987. Similar efforts to develop creative solutions could eliminate, or reduce, the severity of all of the pollution problems faced by modern society. Conclusions. It is clear that pollution has had severe impacts on wildlife populations. The extent of contamination is global, with synthetic organic chemicals, toxic metals, and acid deposition present at even the most remote portions of the Earth. Furthermore, it is probable that numerous effects of pollution on wildlife have not yet been detected, due to the relative youth of this field of study. In reality, most types of pollution are unnecessary, and the activities that pollute the environment can be modified such that the amount of pollution occurring is greatly reduced, or eliminated, provided we are willing to pay the costs. Alternatives to the organochlorine pesticides have already been developed, including a new generation of pesticides that are less toxic, and degrade more rapidly, in the environment. Methods of pest control have also been developed, that reduce or eliminate entirely, the need for use of synthetic chemicals. Under this integrated approach, farmers use chemicals only when necessary, rather than as the first, and primary, line of attack. The interest in pesticide-free farming, and gardening, is increasing as the side effects, and true costs, of the chemicals become known. The wreck of the Exxon Valdez demonstrated many ways in which similar catastrophes may be prevented, or better managed in the future. Some of these include, the use of double-hulled tankers, more careful tracking of vessel traffic, and better preparedness on the part of oil companies, and governments, for large spills. Decreased consumption of fossil fuels would be the surest way of reducing the risk of the occurrence of future oil spills. Air pollution from the metal processing industry, and fossil fuel burning power plants, is the primary source of both toxic metals, and acid rain. Technology is available that can sharply reduce the amounts of these substances that are released from smokestacks. Reduced consumption of fossil fuels is also a potential means of achieving diminished emissions of toxic metals and acid rain. It is our use of materials and energy that lies at the root of most pollution problems. Historically, the environment has been treated as an infinite receptacle for our wastes. Some of the disastrous ecological consequences of this ignorant attitude are now apparent. A combination of awareness, creativity, and a willingness to modify our lifestyles will allow us to curtail the threat that pollution poses to wildlife and other species, including humans.